I am Dingtian Zhang, a PhD student at Georgia Tech UbiComp group. Today I'm presenting OptoSense towards ubiquitous, self-powered ambient light sensing surfaces. This interdisciplinary work is done in collaboration with a number of colleagues and my advisor Gregory Abowd at Georgia Tech. Human activities, directly or indirectly, block the path of ambient light incident upon surfaces of everyday objects, creating interference patterns that can be captured by photodetectors on these surfaces. A photodetector can detect the presence of an object through changes of ambient light intensity. The detection is affected by the size, distance, and opacity of the object. An optical mask that restricts the field of view of a photodetector can tune its detection range. We present OptoSense, a general-purpose, self-powered sensing system that senses ambient light at the surface level of everyday objects as a high-fidelity signal to detect a wide variety of implicit human activities and explicit user interactions. OptoSense system consists of a flexible imaging surface for sensing and energy harvesting from ambient light, and a control circuit for power management, computation, and wireless communication. It supports 0D, 1D, and 2D sensing dimensions that conform to complex surfaces with varying sizes. A 3D printed flexible optical mask is used to tune this field of view. All of these are self-powered by indoor ambient light. OptoSense enables a broad spectrum of applications, all achieved with onboard computation using low-complexity rule-based algorithms. We create a design framework based on activity type, sensing dimension, field of view, and sensing perspective. All the parameters generate a rich application space from different variations. We include previous work that leveraged ambient light sensing to support activity recognition, indoor positioning, and gesture input on wearable devices. We show a list of possible applications in the design space, including representatives that we demonstrate and evaluate under different lighting conditions. 0D OptoSense can detect open-close state of a door or a pill bottle with 100% accuracy. 1D OptoSense can classify 4 types of liquid with 90% accuracy and detect liquid level with an average error of 5.6 millimeter. 1D OptoSense can also detect walking activity and do step counting with a 99% accuracy under dynamic ambient light. 2D OptoSense supports continuous multitouch tracking on a surface. Our 12-participant user study showed a decreased average error from 8 to 4 millimeter as the sensor density increases. 2D OptoSense can also support hover gesture input in 4 directions. Our evaluation showed an increased accuracy from 82 to 95% as the sensor density increases. These enable self-powered interactive surfaces for note-taking, rapid input, or music control. Using the optical mask, OptoSense can detect human presence at 1.4 meter, detect indoor traffic directions, and hover gesture input at longer distances with 90+% accuracy. We also demonstrate the feasibility of organic semiconductor-based ambient light sensing surfaces, which offer a path towards much thinner and flexible form factors, being amenable to additive mass manufacturing processes that drive down the cost of ubiquitous deployment. In the end, I would like to thank my amazing team of co-authors from different disciplines and institutions, Tavener and Yiming for their contributions, our participants, reviewers, and all of you. Thank you, and I'm happy to take any question.